Chapter 10, two-sample tests. So what you need to know about the difference between Chapter 10 and Chapter 9 is that now we're dealing with two-sample testing, and then now instead of having three situations, so in Chapter 9 we have three situations, so now we have four situations. We have population mean with independent sample, population mean with related sample, population proportion, and then population variance. So first situation is population mean with independent sample, and how we usually identify that is basically we look at the sample size. Usually when the sample size are not equal, then we have situation 1. Second situation is when we have the related sample or related pair. And how we identify the situation is usually they have the same sample size because they're the same person filling in the survey. Third situation is when we have population proportion. So proportion is just your percentage. So whenever we see percentage and we have two groups of percentage, then we know this is proportion. Last one is population variance. When we're looking for variance, then we know that we're in the fourth situation. Example 1, you're a financial analyst for a brokerage firm. Assume both populations are approximately normal with equal variance. Is there a difference in the dividend yield between stocks listed on the New York Stock Exchange and NASDAQ at the 5% significance level? You collected the following data. So we're given the data here. We have the number. So this is the sample size for the New York Stock Exchange and NASDAQ. Sample size, this is N1, N2. And we're given the sample mean and then the sample standard deviation. So in Chapter 10, we asked the same two questions that we asked in Chapter 9. So those two questions are, the first question is, which testing are you dealing with? So that's the first question that we're asking. And how we know which testing we're dealing with is because we're looking for the word difference here. So difference means that we're looking for two tails. We're looking for equal or not equal. Are they the same or are they not the same? So that's why we know this is two-tail testing. So that's the first question. Second question that you need to ask is which situation you're in, and how we know which situation we're in is because our sample size are different. N1 does not equal to N2. So what that means is that there are two independent samples. So we're in a situation where we have two independent samples. So once we know which situation we're in, once we know we're in an independent sample situation, and once we know that which testing we're dealing with, we're in the two-tail testings, and we go back to the formula sheet and we identify what our H1 and H0 will be. So in the formula sheet, we know that we're in an independent sample, and we know that we're dealing with two-tail testings. So once we have those two questions sorted out, we're in the independent sample, we're dealing with two-tail testings, then we're given that the hypothesis is that mu1 minus mu2 equals to 0, and then mu1 minus mu2 does not equal to 0 for the H1. So we put that directly into the answer. So that's why we have in the answer here, mu1 minus mu2 equals to 0, mu1 minus mu2 does not equal to 0. This is what H1 is what we want to prove. We want to prove they're different. So we want to prove that the mean 1 minus mean 2 does not equal to 0. That's what we want to prove. So in part B, we're calculating the test statistics. We're using test statistics as our decision rules. So to calculate the test statistics, I gave you the formulas here. And what you need to know is that in order to calculate the test statistics, you need to calculate the pool variance by using the formula here. Once you calculate the pool variance, you substitute that into the formula to calculate the t-statistics, and you're going to get 2.04. So you can do that algebra on your own time. And once we calculate the t-statistics, what we know is that since we're dealing with two-tail testings, we're going to compare the t-statistics with the t-critical. So t-statistics, we get it from the algebra above. T-critical, we're going to use Excel, the formula in Excel that we did in Chapter 9 to calculate the t-critical. And the reason why we're using t-distribution is because we're given sample standard deviations. So in Chapter 9, what we talked about is that whenever we have sample standard deviation, whenever we have the mean with sigma unknown, so whenever we don't have the population standard deviations, so if we don't have the population standard deviation, that means we have the sample standard deviations. So whenever we have sample standard deviation, what that means is that we're using t-distribution. So we calculate t-statistics, and for t-critical, we use the t.inv. For p-value, we use t.dis. So same idea in Chapter 10. In Chapter 10, we're dealing with sample standard deviation, so therefore we're looking at t-distributions. So we're using the t.inv to calculate for the critical value. And since this is two tails, so for critical value, from Chapter 9, we know that we're using alpha over 2 and then 1 minus alpha over 2. That's what we put into the probability into the t.inv. So that's why when we put it into t.inv, we put 0.025 and then 0.975. Alpha is 5%, so alpha over 2 is your 2.5%. And then 1 minus alpha over 2 is your 97.5%. And then your degree of freedom, the formula here, I give it to you, n1 plus n2 minus 2. So we have 21 plus 25 minus 2, that gives you the 44. So we put that degree of freedom in. And then we're going to get the plus minus 2.01 as our t critical. Once we have t statistics and once we have t critical, then we compare them in absolute value. We know that t statistics is greater than t critical, so therefore we reject h null, we accept h1. We're accepting that the mu1 minus mu2 does not equal to 0.